So this seminar is uh, the first motivation is that this seminar is inspired in three joint works with Yuri Martins and Rodney Josué about the classification problem of extensions of Yang-Mills type theories. Two of them are, we have preprints of them. One is still in progress. And the reason of why consider extensions of the standard model is because the standard model is probably an effective theory of a more fundamental theory. This is something that is clear today in the literature. And in fact, throughout the years, a lot of models have arisen in order to explain physics beyond the standard model. Uh, some of them are models that consider a higher dimensional space-time, like string theory, models towards quantum gravity, extensions based on symmetry breaking, like the standard model extension, and even models that based on symmetry enlargement, like minimal supersymmetric model, and so on. And our interest here is not on any particular model, but on a classification of the main features that realize them as extensions. So the search and the classification of these extensions relies on the following questions. What mathematical objects does the standard model depend on? And can these mathematical objects be extended in some sense? Uh, in order to answer the first question, let's see how the standard model is made of. It is composed by four components: the Yang-Mills sector that describes the dynamics of gauge fields. This is the part of the theory that deals with force fields, uh, interactions between gauge fields and matter fields. The Higgs sector that describes the interaction of the Higgs field with the gauge fields, and also describes the Higgs potential. And the Yukawa sector that describes the interaction between Higgs fields and matter fields. Here, as the title of the seminar indicates, we restrict ourselves to the Yang-Mills sector. More generally, we consider Yang-Mills type theories. So what is a Yang-Mills type theory? Uh, what object does it depend on? So a Yang-Mills type theory is given by an n-dimensional compact orientable semi-Riemannian smooth manifold. This is the space-time. A real or complex finite dimensional Lie group. This is the gauge group, or the group of internal symmetries of the theory. A principal G bundle over M, which is called the instanton sector of the theory, and an action functional defined on connections of P, which is given by this function, where this pairing is defined on horizontal and equivalent forms. And it can be an arbitrary R linear pairing. This is what uh, differentiates the Yang-Mills type theory from the usual Yang-Mills theory. we are allowing the pairing of the theory be arbitrary. So you know, we have seen what objects the Yang-Mills theory depend on. So in order to answer the second question, how these objects can be extended, we are our context of extension. We consider the following sense of these these extensions of objects. Uh, Considering a larger gauge group, adding a correction term in the Yang-Mills type action, or considering deformations of the Yang-Mills action function. Soon I will explain what I mean by deformations. The first two is intuitively clear, but the three I will explain. Actually, we will see that correction terms and deformations are related. And I want to point out that there are other contexts of extensions in the literature of extensions of Yang-Mills type theory, like considering a higher dimensional space-time, or replacing the Lie algebra G by a general algebra A. And this, we are not working here, only these three senses above. So a deformation of a Yang-Mills type theory SG is a theory hat S such that is the limit of a family of theories hat SE I, such that the first element of the family restricted to the domain of the original theory is equal to it. Here, the family and the deformation can be defined in a larger group, larger than the larger domain than the connections. There is the domain of the original theory. Usually, this sequence family is made of partial sums, so that they are sums of another functions like that, where these lambda j are parameters, so that f0 lambda 0 equals 1 for every value that this lambda 0 can take, and the limit of fj lambda j when lambda j tends to 0 is 0. And also that the first element, the first partial sums that are equal to this S0 by definition uh, equals to the original theory a composition of the original theory with a lambda map that maps the configuration, some configuration phi lambda j in the domain of the deformation to its limits of lambda tending to 0. So this map is like a restriction of the domain. It is like you take a configuration and make it do not depend on the lambda, tends the lambda to 0. So you in order to obtain a connection, an element of the original domain. This implies that we have the following decomposition. You have your deformation as the original theory, compose, composition of the original theory with this delta, plus a correction term. So the conclusion is that the deformation is a map possible defined in a domain larger than connections, and it is equal to SG except for the correction term and the presence of the lambda map that acts as a restriction of scale. So our context of extension, which will be defined, aims to consider both of these aspects, restriction of scales and adding correction term. And, in principle, the correction term of the deformation is defined in the entire domain of the deformation, but we will consider that the correction can also have a restriction of scale on it. So the deformations is based on restriction of scales. Corrections is based on the addition of term in the entire domain, and our extension will be additional term in some scale. This is the unification. And to define our context, some preliminary definitions and facts are that let G be a Lie group. We define the basic extension of G as another Lie group, hat G, and a monomorphism I. So a basic extension is just a larger group so that G can be viewed as a subgroup. And let P be a principal G bundle over a manifold M, and I be a basic extension, fixed. There are the following facts. The classification theorem of principal bundles implies that P is classified by a multiple class of continuous map from M to BG, where BG is the classifying space of G. This is just a specific topological space that it exists for every G, and it's not important. The important thing is that P is classified by some homotopy class of continuous maps. And B is also functorial. So we have that this hat F, which is the composition of B applied to the basic extension, and the composition to F with it shall be not what we hear, but a function from M to B hat G. This function hat F classifies a principal G bundle hat P. And some facts is that the classification theorem is realized by pullbacks of bundle, and from universality there exists a bundle morphism I from P to hat P, And moreover, this morphism is actually a monomorphism due to the stability of monomorphism by pullbacks. The important thing is that given a basic extension of the group, you have a natural extension of the bundle. So the unification approach of the extensions is what follows. So for us, an extension hat S hat G of Yang-Mills type theory is given by a way to enlarging the gauge group, which is just a basic extension, a domain larger than that of the original theory, possible larger, which is an equivariant extension of the space of connections, which is equivalent to a subset, this hat con, which uh, is a subset of equivariant forms, which is invariant by the action of pullbacks of the automorphism group of P, hat P. This invariation is what we mean by equivariant extension. And an extended action functional defined in the in this larger domain, which we also call as extension domain, extended domain, a correction subspace. We want to not consider the entire domain of the extended action, but a restriction of scale of it. So we take a correction subspace where the extension will be realized as a sum of the original theory and a correction term. A correction subspace and a correction subspace is just a set of the extended domain, not or there is not an other structure on it, just a subspace. And a correction functional defined in this correction subspace. Again, this correction functional there is a restriction of scale on it, and the restriction map such that the extension is a composition of the original theory and the restriction map plus the correction. The difference between the deformations is that in that case, the whole deformation, the whole theory is equal to the sum, to this decomposition. Here we have that the extension is this decomposition just on a restricted subspace. So an example of this construction is the Higgs mechanism that I will present. First, I will recall the classical description of the Higgs field. So let G be a closed Lie group of hat G. Then a classical Higgs field is a section of the associated bundle E, where the action of hat G in this coset is the natural action by left multiplication of coset. The space of all Higgs fields is denoted by Higgs. And there is an interesting remark that there is a one-to-one correspondence between Higgs fields and G reductions of hat P. So when such a Higgs field exists, and we have a classical field theory depend on it, on hat P, we say that the geometry, the hat G symmetry is spontaneous broken to G symmetry, because it implies an extension of a G reduction, a way to reduce the structure group of the bundle. So our objective is to construct an extension S of S hat G by the addition of equivariant correction C that depends of a connection and a Higgs field. But our definition extension says that the domain of an extension is a subset of forms, but a Higgs field is not a form, is a section of a associated bundle. So we need need a way to pass from this section of this bundle to connections. This is made by the following steps. We assume the existence of a map from this coset space to the Lie algebra of hat G, satisfying the following compatibility relation of compatibility of the actions, where the action of hat G is made by the adjoint representation, and the action of the coset is left multiplication. This relation gives us a bundle morphism between the associated bundle E and the adjoint bundle E G, which is fiber-wise given by theta. The compatibility relation is necessary because you need to, we are trying to these bundles are the fibers of these bundles are defined by different equivalence equivalence relations. So this map is well defined precisely when the theta such there is a compatibility between the actions. And applying the section functor gives us a map from sections. So given a connection hat D in hat P, we consider the covariant derivative induced in the adjoint bundle, and we consider the image of the following composition. Here we are using isomorphism of forms in the adjoint bundle and equivalent forms in the principal bundle. And we defined this theta 1, this space, as the union over all connections of the image of this map, which is a subset of equivalent forms, and is a equivariant subspace, invariant by the action by pullbacks of the automorphism bundle. This is because we are working with equivalent forms. The covariance derivative is equivariant. The compatibility relation also makes this theta star be equivariant, so all of here, so all the maps here are equivariant. So the image is equivariant and also the union. So we set the following data for the extension: a trivial basic extension, recalling that we are not trying, in this example specifically, we are not trying to extend the gauge group. The Higgs mechanism is about just to add a correction term on the original theory. An extended domain given by the union of the previous sets and connections. This is just to this extended domain contains the connections. In this case, this is not really important. A correction subspace given by C1 by theta1, and a restriction map given by, you take some of this covariant derivative and maps to the connection. This initial, this is not well defined in this map, but you can well define it by the using of axiom of choice. And for any equivariant correction, we can define an extension such that restricted to C1 is what we want. And in particular, if the correction term is given by this, which is essentially the you have applying the pairing in the covariant derivative of phi, then we call hat S as a Yang-Mills Higgs type theory. So one of the in a physical context, one case in which this such the compatibility relation that we asked for is satisfied is on the Toft-Polyakov monopoly description, where we have G as SO2 and hat G as SO3. This is precisely what makes that we can pass from a Higgs field to a section of the adjoint bundle. This is a physical example of the compatibility relations is satisfied. And I want to talk about an existence problem of extensions. That we have seen that if S hat D is a Yang-Mills type theory, then there exists an extensions hat S, hat G, which is the Yang-Mills Higgs, and associated to the basic extension. So again, the Higgs mechanism aims only on the addition of a correction term to the action function. We are preserving the gauge group. Thus, we search for a result as the following. Let's SG be a Yang-Mills type theory. Then every basic extension induces a non-trivial extension. So for every way to enlarge in the gauge group, you can define a non-trivial extension. So the idea of the proof of this extension existence problem is that first Given a basic extension, we first define what we mean by a basic extension of SG. We denote this space by basic X, and it turns out that every element on this space induces a canonical pairing on horizontal equivalent forms of het P. The second step, we show that every basic extension induces a decomposition of every Yang-Mills theory, restricted to the space of reducible connections. I will explain what this space is, but here we this decomposition is for every Yang-Mills type theory. So we are trying to extend a Yang-Mills theory by another Yang-Mills theory. This another Yang-Mills theory is with gauge group, with the larger gauge group. And the choice of a basic extension allows us to write this S0 as the composition that we are looking for. So the first step for this is given a basic extension. We first defined the basic extension of the theory, and let SG be a Yang-Mills type theory, and denote this pairing by this. So we defined a basic extension by a basic extension of the group and an extension of the pairing as below, where this I star I push forward is induced by the application of the Lie functor on the basic extension of the group. So we are extending the pairing by, and a lemma, the main lemma of the proof is that the space of basic extensions is non-empty, and every element of it induces a canonical pairing. And this pairing can be chosen as this a composition of the extended pairing that comes from the basic extension of the theory by definition, and the push forward of this monomorphism of bundles. Né? And second step, we first defined that what is a reducible connection. So a G connection het D on the bundle het P is reducible if there exists a smooth pointwise decomposition relative to the vector space isomorphism. This vector space isomorphism, where dA for every point A, D takes its value in the Lie algebra of G, and EA takes its value in the coset. The space of reducible connections will be denoted by this red. And since equivariant forms are invariant by pullbacks, it follows that the pullback of D by the monomorphism of bundles defines a G connection of P. So recalling that dA is a form from T hat P from to G. So for every connection hat G, reducible connection, we have the decomposition, and we can write the curvature of this connection as this by definition of curvature, and uh, by the decomposition we can write like that and define these terms hat fd uh, as uh, as this, such that the pullback of hat fd is a curvature of the previous connection of on P, and theta is defined by that, is called the torsion of T. So applying the pairing in the last, in applying the pairing in this decomposition here, we have this where C is the remain terms, and it follows that the first term uh, it's equal to the first equality is by definition of this first map, and the second equality is by the observation made before. The pullback of the curvature is the curvature of the pullback, and the third equality is the fact that this third pairing is an extension of the original pairing, and but the f of I push forward D is a connection of P, so it's takes values on G, so this is equal to the original pairing. So the extension uh, is equal to the original function on the original domain. So we now simply define the restriction map as the projection hat D to I push forward D. So we have exactly what we want. So the first term here is the Yang-Mills theory, composition of the Yang-Mills theory with this projection, and a correction term. So this ends the proof. So the last part of this seminar, I want to comment about the space of extensions. As is some brief comments. So let SG be a Yang-Mills type theory and fix a basic extension. Let X denote the space of all extensions of SG whose underlying basic extension is I. And note that an extension is a triple of the extended action functional, the correction, and the delta map. All of these maps valued in spaces where addition is defined. Actually, the lambda map is defined on the space of connections. That is which is a thin space over the vector space of equivariant horizontal forms. But you can always fix a connection so it becomes a vector space, and addition is defined. And the space of extensions has the following structures: commutative monoid structure that for every extended domain hat con relative to the basic extension. Let this space X be the space of all extensions which has hat con as extended space. Then this space is an abelian monoid with the sum operation given by this we defined the sum of the extensions by that, and the correction subspace of the sum is the intersection of the correction subspace. And this is the operation, and this monoid is typically not an abelian group. To see that, we could we have a natural candidate for the multiplication by scalar, by a scalar C, by pointwise multiplications of the triple, of each element of the triple that defines an extension. So, however, these pointwise multiplications are not compatible since the functional is not R linear, but typically quartic. So what I mean by that is that by pointwise definition, we would have this first equation, but on the other hand, by definition of extension, we'll have this, and the Yang-Mills action function is typically not R linear. So in general, assuming a symmetric pairing, we have SG applying to CD as this expression, and while C SG is simple the pointwise multiplication, and these expressions are equal when C is a root of some polynomial. This polynomial over some ring of functions. And in general, -1 is not one of these roots. For example, if G is abelian, then d edge d equals to 0, and the polynomial takes this form, whose roots are t equals 0 and 1. So we can't multiply. This is the conclusion that C equals. You are recording? Or
Yeah, yeah, it's okay.
This is the conclusion that we have an obstruction on the abelian group structure. That C equals minus 1 is none of these roots of the polynomial. And other structures that I will just comment is that we have for every group action of G on the real numbers, we have an induced action on this space of extensions with extended domain het con. And if the action is additive, then the induced action is also additive with respect to the commutative monoid. And for every ring, we have in every additive group action, which is we can call this additive group action as a G-monoid structure in R. We have an induced RG module structure. RG is the ring group. So we can ask for a bundle structure of this space. So let ED be the set of all extended domains, and we have a projection of from the space of extensions to the space of extended domains assigned to each extension its underlying extended domain. This is a natural projection, and the fiber of each extended domain is just the set, just the set. And we have already seen that each one of these fibers has a RG module structure. So the question when there is a RG module bundle structure arises, but probably this bundle is not locally trivial. This is because naively we can expect that different extended domains have different sizes. It can be even different if it's finite dimensions, can be different dimensions, and would produce fibers with different sizes. So there is not a typical fiber. However, we conjecture that it can be embedded in this trivial bundle, which is a RG module bundle also. This idea is inspired in the fact that we can construct in the first paper a specific map. The name of the map is not important, but it is this I star. But the important thing that this map makes the following diagram commutative. So in particular, if this map is continuous, I am omitting choices for the topologies, but there is also a specific choice of topology for every one of these sets. And if this map I star is continuous, this gives us a bundle morphism, and we can try to find in specific topologies conditions for the continuity of this map, and also a way to define a continuous section S. of this map in such a way that the previous diagram extends to the following commutative diagram. So if such section S exists, and if this section is continuous, we will have an bending of the bundle on the trivial bundle. And as a future research, the existence of R and G such that this map is continuous is one conjecture, one of them. And we found sufficient conditions for the existence of S. But they are that this space, which is the typical fiber of the trivial bundle, if this fiber is injective as RG module, and if the fibers for every extended domain, except maybe for the first one, obviously, is projective as RG module. These are conditions for the existence of S, but the validity of these conditions, the existence of such R and G is another conjecture. So this is one thing that we intend to work on, and it is very interesting result because you are relating the problem of classifying extension, the space of extensions, to the stud of bundles, specifically bundles of groups, bundles of rings, and that's it. What I wanted to talk about. This is they are the references. Thanks.
Okay, thank you, Luis, for the nice talk. Let's all unmute themselves and thank Luis, please.
Thank you.
I will stop the recording now.